Hello guys again, and this is another version of the part which I recorded without image. So we have just a little piece of lecture 3 left. And since we learned how to multiply matrices, I want to show you a nice multiplication between two strange matrices, which we are going to use in future a lot. So let's consider matrix A, which has dimensions n, let's say m, it's better to do first letters m by n. That's just a general coefficient matrix. I'm going to label my coefficients with standard indexes, 1, 1, lots of other coefficients, 1, n. So we have n columns, and we have A, M1, M rows, and over here, A, M, M. So let's consider a standard, just more general matrix A. Another matrix I want to consider is matrix which I'm going to label. This matrix is going to be just one column. That's going to look like this. The first element is going to be x1. There are going to be plenty of other elements, and the last element is going to be xn. This matrix has n rows and just one column. It's not the same as matrix A because it has m rows and n columns. And one more matrix, which I'm going to label as matrix B, which is also going to be just a column. It's going to have slightly different dimensions from my matrix X. It's the first element is going to be B1, just one index. And the last element is going to be BM. Look like M actually. Maybe I should erase it and do a better M. BM. So two column matrices X and B are not same. This one, the first one has n elements, the second one has m elements. For m equals n, of course, they're going to have same amount of elements, but here we can generally have different amount of elements. Now, what I'm going to do, I'm going to multiply matrix A by matrix X. So I'm going to write down A multiplied by X. And how it's going to look in real. So I'll need to copy this matrix A, 1, lots of other elements, 1n, and kind of lots of other elements. And I'm going to write down my matrix X over here, which is x1, lots of elements in between, xn. Let's see what we are going to have as a product. You guys probably remember to multiply two matrices. We are going to take a row of the first matrix and multiply it by the column of the second matrix, right? Because we do have only one column here, we are going to just do one multiplication, right? So in this case, what we are going to have, element 1, 1 is going to be multiplied by x1. And I did not write here element 1, 2, but let's imagine that we have 1, 2 is going to be multiplied by element x2. And it's going to continue until you reach the very last element, a1n multiplied by xn. And what I have actually, that's just one element of my product, right? And this element is going to be a whole linear equation. The only missing thing here for this linear equation is equal sign and the right side, right? Why don't we put over here equals B1? Well, again, the product over here is going to have dimensions. Remember, these are dimensions, the dimensions of A matrix, and dimensions of X matrix are n by 1, right? Remember, when we multiply matrices, we are going to kind of eliminate inner dimension, this one, and keep only outer dimension, this one and this one. So final dimension of the product result is going to be m by 1. So it's going to be like m rows and exactly 1 column. And that's what we have over here exactly. So guys, you probably see where I go. If I continue this multiplication, like multiply my second row by this column, I'm going to get my second equation. 1, 2, x1 plus, wait, sorry, not 1, 2, but 2, 1. A 2, 1 by x1 and until I get a2n by xn, and I can make it equal to b2. And continuing the same way, I'm going to get my last equation, am1 x1 plus whatever amn xn equals bn. So basically, guys, what I got is a system of equations. It's a linear system, m equations and variables, right? And basically what we have, it's a new way to write down this system using matrices. So actually what you see on the right side over here, we do have like three terms, P's, right? Which are making up this column. So we can actually write down this linear system as a product between matrix of coefficients, matrix of unknowns, and B. Well, B not necessarily supposed to have all numbers. It can be zeros, right? And that's going to turn into homogeneous system. But in our case, generally, we can have non-homogeneous system. And that's how we are going to write down system of linear equation if we are in a hurry. We just need to remember that this equation is not actually like multiplication of like two numbers equals the third number. It's multiplication of matrix by another matrix and it equals to the third matrix. Okay, so the way to write down the system of equations. By the way, sometimes I'm going to write it down even this way. A small x equals small b. And that's going to mean the same if I say that A is the matrix of coefficients. Okay, we're going to meet this way to write it down later in future. For right now, we just need to know that if you see it, sometimes it's not just like multiplication. By the way, equation looks very much like linear equation, right? Like if you compare it to ax equals b, you know how to solve this linear equation. If your unknown is x, to find x, what you will need to do? You need to divide b over a, right? How we solve it. Here, for matrices, is going to be slightly more complicated, but we are going to have something similar to this. Now, last new thing in this section is transpose over matrix. So I'm going to leave transpose matrix. What is transpose over matrix? Well, imagine that we have matrix A. We can create matrix A transpose using the next rule. The rule for A transpose is that element ij of A transpose is going to be equal to element ji of original matrix. So basically, we are going to switch. Remember that I is labeling rows and J is labeling columns. We are going to switch rows and columns in our new transpose matrix. I'm going to show it on a simple example of just one column. Imagine that your matrix A looks like one column matrix which has 3 rows and only elements 1, 2, 3. How A transpose is going to look? A transpose is going to look like the same matrix, just instead of column, it's going to be a row. Well, you can just check it. For example, this is element 1, 1. It's still going to be element 1, 1 for transpose, right? Just because indexes are the same. But element 2, 1 is going to become element 1, 2 for transpose matrix, and so on. Now let's do transpose of something more complicated. Another example. Let's consider matrix B, and it's going to have, instead of just one column, 3 columns. and 2 rows. How transpose is going to look? Transpose of this matrix is going to look like this. We're going to take the first column 1, 4, right, and make it the first row 1, 4. Second column 2, 5, second row. And the third column 3, 6. Well, basically, well, it's not necessary to do it column by column. You can do it row by row. Doesn't matter actually. Just understand that find transpose is to change rows and columns in the matrix. It's like reflected over main diagonal. And what else do we need to know about matrices? Trace of a square matrix. We're not going to use trace a lot, but we need to know what is this. Trace of a square matrix. Trace of a square matrix. Imagine that we do have a square matrix. Square matrix means that it has the same amount of columns and rows. 2 by 2, 3 by 3, 4 by 4, and so on. What is going to be trace of this matrix? I'm going to first give an example and then give you a general formula. So imagine that we are dealing with 2 by 2 matrix, and the matrix is going to look like this: 1, 2, 3, 4. So what is going to be trace? We are going to add elements on main diagonal like this too. So I'm going to write down trace of A is going to be equal 1 plus 4. I'm just adding elements on main diagonal, and that's going to be just one number. So trace is one number. In general, trace is going to be trace of matrix A, n by n, is going to be equal. I'm going to use sigma notation, guys. I don't know if you are familiar with it or you just kind of. So it's going to look like this: from I equals 1 to I equals n. We're going to add elements on main diagonal. Elements on main diagonal are going to have same indexes like 1, 1, 2, 2, 3, 3, 4, 4, and until you reach nn. This is just summation. So I'm going to expand it a little bit for those who don't like sigma notation. So it's a sum of elements on main diagonal. And it's just one number. It's not very informative, but sometimes it's enough information to make a conclusion about the matrix. Well, I don't know. I don't think that you will need more examples of how to calculate trace. You just need to know the definition. Okay. And I think that's all for this part of a lecture, which I kind of did not record. Hopefully you like it. And I'm going to hope that this one is going to be recorded better. Thank you very much.